Hello everyone, this is our last topic, cooperative games, but we deal only with one specific topic of cooperative games. Cooperative games includes a lot of material, and I encourage each one of you once to study cooperative game theory. However, I take one specific topic, that actually the people that dealt with that topic got a Nobel Prize in economics for that in 2012. The two persons that got the Nobel Prize is Lloyd Shapley and a giant game theorist, one of the, together with Nash and maybe Bob Aumann, they are the three very leading persons in game theory. So that's Lloyd Shapley. He died about 2 years after he got the Nobel Prize at the age of 92 or 93. And the other one, together with him, got the Nobel Prize is Alvin Roth from Stanford University. Alvin Roth mainly established the theory, used the theory established by Lloyd Shapley and his co-author, David Gale, and make it a very applicable, and these days everything is even very applicable to kidney exchange or liver organ exchange. David Gale did not get the Nobel Prize. He did the theoretical part together with Lloyd Shapley. Actually, he brought up the problem, and together with Lloyd Shapley, they got the solution. But he died he was 85 or 86 years old when he died. And as you know, dead people do not get Nobel Prize. But Gale Shapley is the generating of the problem, and Alvin Roth was mainly applied that in the real world. I'll tell you exactly about the problem and everything. But the problem there deals with market without actually good, but it's two-side markets. It's matching, like matching boys to girls, etc. So, for instance, you want to match employers to employees, hospitals to residents, students that finish their degree, medical degree, and become doctors, medicine doctors, they have to start working in hospitals. So there is a problem. Hospitals want specific residents. Residents want maybe specific hospitals. How to do it? Universities to applicant. A student try to get to a lot of universities, and university attract a lot of students. So how to make the matching between university to applicants, hospital to residents, employers to employees. And that has to do with matchmaking. This is as opposed to single-side markets that you have teaming up like roommates and stuff like this. But we are talking about, let's say that I need to match everyone partially to everyone. You have a group of students, and you want to match them to get dorms. To get dorms in the campus. This is actually single-sided because it's not like there are two groups, women and men, employers and employees, and the two groups are completely disjoint, and we want to match them one to one or one to many. By the way, so in that case, we are going to talk a little bit about, not a little bit, mostly about matching one to one. But this is not very applicable. It's, if you want to match husband to wife, so that is applicable. But if you want to match employers to employees, Every employer works for one employee, but one employee may hire several employers. We will call that polygamy. Monogamy is when you match, let's say, boys to girls, okay, one girl to one boy and one boy to one girl. This is a two-sided market, and this is monogamy. If we don't care about girls, boys, but we have to somehow to match all of them, this is one-sided, single-sided market. But we are going to focus on two-sided markets. I'll make some remark about the single-sided market later on. So let's start with some problem that bothered, for long years, the hospitals and the interns. So the matching market of hospitals and the medical interns in the USA. Every year, around 20,000 interns, complete their medical degree and become doctors, and they have to go to hospitals. So what happens with the matching between interns and hospitals? So the tragedy of the doctors, that's phase one. So I'll go through the story because it's interesting. The internship was first introduced around the turn of the century. I'm talking about the previous, I have to change it, the previous century. So we are talking about early 1900. Competition by hospitals for interns manifested itself in a race to sign employment contracts earlier and earlier in a medical student's career. Also now, when you go to study MBA, already companies comes to the campus, interview the students, and they used to come in the last semester of the MBA. Typically the MBA takes 2 years, so they came the last semester of the second year, but then they wanted to find the better one and to let them sign to give them an employment contract, so they start coming in the first semester of the second year. And then some of them now coming in the second semester of the first year, just because of competition. So hospitals also compete for good interns, and they start coming earlier and earlier with contracts to the good students. The date by which most internships had been finalized began to creep forward from the end of the senior year of medical school to we'll see in a second. This was regarded as costly and inefficient both by the hospitals. First of all, it's not efficient for the hospitals. Why? They had to appoint interns without knowing their final grades or class standing. They wanted them very early because they were afraid that some other hospital will come and pick them up. So they were rushing to offer contracts before they knew how good the student is. Moreover, the students, once you get a contract, you don't need to study very hard because I have a contract. So it's not efficient because you get students that are not very, very hard working and do not get may miss some material, or they don't exert proper efforts, knowing that they have no problem, they got a contract. And by the students and medical schools who found that much of the senior year was disrupted by the process of seeking desirable appointments. So they start, because of the competition, they start coming earlier and then earlier, and they moved from the last year to the senior year, to the previous year. Okay, and the beginning they came to the senior year, but then because of competition they start coming earlier and earlier. Okay, so this is inefficient in the sense that you give a contract to someone that you are not sure about his quality or her quality. And in addition, students that get the contract, they don't exert proper efforts because, we said. In 1944, the standard appointment date has now been advanced on the school calendar to the beginning of the junior year, from the senior year. Okay, so instead of hiring them or give them a contract at the end of the senior year, they start approaching and giving contract the beginning of year before. A happy end to all this mess? The problem was solved. I would put quotes, solved, in 1945, when the medical schools in the Association of American Medical Colleges, AAMC, undertook not to give out before some agreed date any information to hospitals regarding students' abilities. So let's fix the date. Before that date, you don't get any information about the students, and therefore you are not going, it doesn't pay you to come earlier. The tragedy turns into a farce. A new problem appeared and manifested itself in the waiting period between the time offers of internships were first made and the time students were required to accept them. So you give an offer as a hospital, the student have time to say yes or no. So about that waiting period, there was a problem. What is it? Basically, the problem was that a student would be inclined to wait as long as possible before accepting the position he had been offered. Why? In the hope of eventually being offered getting a better offer, offered a preferable position. So why should I answer today? I got the offer today. Why should I answer today? I'm best off waiting until the last minute. Why? Because maybe I'll get a better offer. So what? Students who were pressured into accepting offers were unhappy if they were ultimately offered a preferable position. So if you say, let's say hospital called you, we need an answer, you felt a little bit uneasy, pressed, and therefore maybe you said yes, and day after you got a better offer, but already you made a commitment. So students, some of them, were unhappy about it. Hospitals whose candidates waited until the last minute to reject them were also unhappy if their preferred alternate candidates had in the meantime already accepted positions. So they are waiting. Let's say I'm a hospital, I give you an offer, you have to answer after 1 week. I wait, you answer in the last minute, and then you say no. So I have to run now to find somebody else. So it didn't work out well. Hospitals were unhappier still when a candidate who had indicated acceptance subsequently failed to fulfill his or her commitment after receiving a preferable offer. So let's say the hospital called me up and I say, yeah, I'm about to accept, give me, gave the wrong impression that they are about to say yes. All of a sudden they got a better preferable offer and they say no. For 1945, it was resolved that hospitals should allow students 10 days after an offer had been made to consider whether to accept or reject it. So hospital gave an offer, 1945. They had to wait exactly 10 days before the students will answer yes or no. For 1946, it was resolved that there should be a uniform appointment date, okay? And they decided July 1st, on which offers should be tendered and that acceptance or rejection should not be required before July 8th. So they nail it down. You get an offer July 1st, you have to answer yes or no by July 8th. You can do it earlier, but by July 8th. 3 years after, by 1949, the AAMC proposed that appointments should be made by telegram. Probably most of you never heard about telegram. That was before you could easily call. You send a telegram. Every word cost money at the time. By a telegram at 12 and 1 minutes a.m. at night on November 15. Okay, so all appointment by telegram. A telegram was supposed to get to you very, very fast. So the telegram was sent at 12:01 a.m. on November 15. So the beginning of November 15, with applicants not being required to accept or reject them until 12 noon the same day. So now they say, no, we don't give you a full week. You have to tell us yes or no. Sorry, in 12 hours. In 1950, the resolution again included a 12-hour period for consideration, with the specific injunction that hospitals and or students shall not follow telegrams of offers of appointment with telephone calls until after the 12 hours grace period. So you are not allowed to call the hospitals before the 12 hours. Okay, so everyone, make it symmetric. You got an offer, you have to answer exactly after 12 hours. In order to avoid these problems and the cost they imposed, it was proposed in 1951 and ultimately agreed that a more centralized matching procedure should be tried. Students would then rank in order of preference the hospital programs. So every student rank what are the hospitals that they liked or to be considered. Maybe you would think of 20 possible hospitals. You say, this hospital is my first best, second best, third best, and blah, blah, blah. And below to these 20, I don't want an offer. Okay, something. Or you could rank all the hospitals. Student would then rank in order of preference, what I prefer more and less, the hospitals programs to which they had applied. Hospitals would similarly rank their applicants. So they send applicants, they rank all the hospitals that they send applications, and all parties would submit these rankings to a central bureau. So not to the hospital, everyone, the students send everything, all their preferences to a central bureau, and the same central bureau got also the ranking of the applicants from the hospitals, which would use this information to arrange a matching of students to hospitals and inform the parties of the results. So they did it in the central bureau. They did it, so not the hospital nor the students. The students just send ranking, the hospital send ranking, and the question how to do it. This procedure was used between 53 and 98, matching roughly 20,000 physicians a year. It was replaced by a new one in 1998. So actually the 1998, the new one is the one that I'm going to teach you. So the National Resident Matching Program, it's called. Okay, so let me try to explain how it works. So welcome to the Spin Dating Club. There are 4 boys, just as an example. You see, here I'm talking about monogamy, because I'm going to match boys to girls or girls to boys, and not what sometimes called the sheikh problem, where a sheikh, Muslim sheikh, can marry up to 4 women, but every woman can marry 1. That is very applicable in the sense that as I said, every doctor can go to work in one hospital, but every hospital can marry or match to several doctors. And so we are going to do it in the most general, but we start with the monogamy case, boys to girls. So there are 4 boys, Adam, Barry, Claude, and Dave, A, B, C, D. And these are the rows, and on the columns will be 4 girls. By the way, it should not necessarily, the number of boys and girls not necessarily should be the same number. We'll talk about it later. Anne, Betty, Carol, and Daisy. These are the 4 girls, 4 boys, and we have to match them. So I would like to know the preference of Adam, the preference of Barry, Claude, and Dave. So that the participants' preference. So here is a table, and Adam likes Daisy the most. She is number 1 for him. He likes Carol second. He likes Anne third, and the last on his list is Betty. So 1 is the best, 2 is the second best, third best is Anne, the last one is Betty. What about Barry? Barry actually likes Betty number 1 for him, Anne number 2, Daisy number 3, and Carol number 4. Claude like also Betty number 1, and also Anne number 2, but between Carol and Daisy, he prefers Carol on Daisy, while Barry prefers Daisy on Carol. Last, Dave, what is his preference? Okay, he thinks that he likes Anne the most, then Daisy the second, then Carol the third, and then Betty the fourth. These are the preferences of the boys. Now I want to know the preference of the girls. So we start with Daisy. Daisy likes Claude the most. She likes Dave as second choice, and Barry as a third choice, and Adam the last one. Here are for all the girls. Carol likes Barry the most, Claude the second, Adam the third, Dave the fourth. And Betty likes Adam the most. The last one is Barry, third one is Claude, and second on the list is Dave. And the last one, Anne, likes Adam the most, like Betty. Like Betty, okay, she doesn't like Barry much. He's last on her list, on her list. However, she prefers Claude on Dave, and Claude is actually second, Dave the third, and this is a little bit different from Betty, who likes more Dave on Claude. But this is the situation, and the question is how to match them. Okay, so you get an example, and we need now to match. Let's say Adam should get someone, then Barry, then Claude, then Dave. So this is an interesting question. And in general, if you have, any number of boys and any number of girls, you may have 50 boys and 71 girls, or opposite, or balanced, the same number, 50 boys, 50 girls. Is there a good way to match them? So this problem was actually David Gale from Berkeley. He had a joint position in math and economics, and he actually asked the question: suppose that every boy, let's say, ranks all the girls, and every girl ranks all the boys, and the question is, do we have a good matching? What is a good matching? I'll tell you now because we are going to see it later. The good matching, let's say stable matching. What is a stable matching? I'll tell you what is not a stable matching. Suppose that a boy was not matched to a girl. Let's say that Barry was not matched to Anne. And that there was some matching. We matched all the boys to all the girls. And let's say that Barry got, I don't know, maybe Betty, but he was not matched to Anne. However, if Barry prefers Anne on what he got, and if Anne prefers Barry on what she got, they will leave their matched, their partners, and will get together. This is not stable. Again, what is not stable? A boy and a girl that were not matched to each other, but they prefer each other on what they got. This is bad because they will leave their partner, will get together, because both of them can improve upon if they go together. And that is, so all the matching collapse. Why? Because if I leave the one that I got, she will have to find somebody else, and that will be a big mess. So what is a stable matching? A stable which is not stable. Okay, that doesn't have this phenomena that there are at least one boy and one girl that were not matched to each other, but they prefer each other on what they got. This is bad. So a stable matching with something which is not done, that doesn't have that bad phenomena. I'll repeat it several times, but that's the idea. Okay, so before we try to solve, let's have some matchmaker's tale. By the way, it's two-sided market. Boys are different from the girls, and we have to match boy to girl. Later on, we'll talk about what happens if you may have gays, okay, and we can rank all of them. That will be one-sided market or single-sided market, because you can. There's no distinguish between two groups, two disjoint groups. We'll talk about it. A Roman lady, so this is the tale. A Roman lady asked Jose Halafta, a famous rabbi and a student of Rabbi Akiva. Rabbi Akiva is a very, very, very famous rabbi in the Judaism, a Jew, that actually learned to read when he was 40, but he became genius. Okay. Who lived in late first century in Tzipori. Tzipori is someplace in Israel, north part of Israel, not too far from the Sea of Galilee. And so the Roman lady asked the famous rabbi, in how many days did the Holy One, God, blessed be He, create His word? How many days He created His word? He answered, in 6 days, as it is written, for in 6 days the Lord made heaven and earth, etc. She asked further, and what has He been doing since that time, after creating heaven and earth? What then? Since then, what did He do then? He answered, okay, let me move it a little bit up, okay, but it's, I can, he answered, a Roman lady, he answered, he is joining couples. A's wife to be allotted to A. A's daughter is allotted to B. So and so's wealth is for so and so, etc. So he's joining couples. Okay. Said she, This is a thing which I too am able to do. It's not a big deal. See how many male slaves and how many female slaves I have. I can make them consort together all at the same time. It takes me a minute to do it. I mean, I don't believe that the Lord has to, since then he is working. It's so complicated. Said he, if in your eyes, lady, it is an easy task, it is in his eyes as hard a task as the dividing of the Red Sea. Remember who divided the Red Sea? That was Moses by the miracle of God. Okay. So it's not easy to matchmake. He then went away and left her. What did she do? She sent for 1,000 male slaves and 1,000 female slaves. Placed them in rows, in 2 rows, and say to them, male A shall take to wife female B. C shall take D, and so on in a minute. A to B, C to D, E to F, blah, 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 blah. Not a big deal. What happened? She let them consort together one night. Okay, so they had to spend one night together. In the morning, they came to her. And now I want to tell you in what shape they came to her, the lady that matched them. One had a head wounded. Another had an eye taken out. Another an elbow crushed. Another a leg broken. One said, I do not want this one. Another said, I do not want this one. As you can see, it's not easy to match boys to girls, but we have to do it. So let's try matchmaking. So let's try to take one example. You know what? We'll match A to A, Adam to Ann, Barry to Betty, Carol to Claude, Dave to Daisy. Let's see how it works. So Adam to Ann. Okay. So we put it in that color that symbolizes the matching between Adam and Ann. And then Barry to Betty, B to B. And then Claude to Carol. And finally Dave to Daisy. Good. So my question, is it a stable matching? Namely, could we find some boy and some girl that were not matched? Like Barry and Carol, or Barry and Ann, or Claude and Daisy, that were not matched. And they prefer each other on what they got. That's the question. If we can, this is not a good matching. So I give you a second to look on the table and try to see if you can find one that a boy and a girl that were not matched, that they prefer each other on what they got. Okay, so let me now try to see. It's enough that you have one couple that are not happy with what they got because they found that they can do better. I say Claude and Betty can do better. Why? Claude got number 3 on his list. If he can get Betty, that's great. She is number 1 on his list. Betty got Barry, number 4 on her list. Claude is better for her, number 3. So Claude and Betty, by going together, both of them can improve their situation. Claude gets, instead of number 3, number 1. And Betty, instead of number 4, she gets number 3. This is not a stable matching. Okay? Adam would gladly swap Anne for Daisy. Okay? Let's start with this. Adam, okay, if he gets Daisy, wow, she is number 1, but she doesn't want him because she gets what? Number 2. Why she should replace number 2 by number 4? So it's not enough. Okay, let's say I want, I don't know, I always forget the name. What's the CEO? Can you help me? Angelina? What's the name of the famous?
Angelina Jolie.
Angelina Jolie. Yes, let's say that I want her. By the way, in my time, the most attractive was Jane Fonda. But let's talk about a little bit later. Angelina Jolie. That's not enough because she needs to want me. So it's not I want a number 1 on my list. Sure, I want number 1 on my list. But the question, what she wants. Okay. So it is not, this does not contradict a stable matching. Why? It is true that Adam prefers Daisy on what he got, but Daisy doesn't prefer Adam on what she got. So there's no way that Adam will go to Daisy and say, Daisy, leave your partner and come with me. But Daisy won't leave Dave too for Adam, who is number 4. Carol too would swap Claude for Barry. Let's talk about Carol. Carol, okay, what did she get? Carol got number 2. She would like Barry, number 1. But Barry, who got number 1 for himself, he doesn't want to leave Betty for Carol, who is number 4. So it's again not a contradiction. But Barry won't leave, but Barry will not leave Betty number 1 for 4. So meanwhile, we did not get any contradiction. But as I told you, Claude and Betty is something different. But Betty and Claude, that's another story. Why? Look, if they get together again, Claude will get his number 1 and Barry will get her number 3 instead of her number 4 that he got before. He for sure improves upon. He's going to get number 3, now she gets number 1. So if this is the matching, before, then Claude and Betty will get together and both of them will be happier than what the matching suggests them. So this is not a stable matching because we found Claude and Betty that were not matched together, but they prefer each other. Claude prefers Betty on what he got, on this, and Betty prefers Claude on what she got. And therefore, they will get together. And what does it mean that Claude moved to Betty? He leaves Carol out, that she will look for someone, and all the matching collapses. Claude prefers Betty 1 to Carol number 3, and Betty would prefer willingly switch Barry for Claude number 3. Betty and Claude object to this matching. And if two can object to the matching is not stable. Stability of matching. A boy and a girl object to a match if they prefer each other to their matched mates. So we can say even a boy and a girl that were not matched, but this is clear that if they prefer each other on what they got, but a boy and a girl that were not matched, object to a match that were not, were not matched object to a match if they prefer each other to their matched mates. A match is stable if there is no boy-girl pair that objects to it, as I said before. So this is the important thing. The object, again, what is not stable, if there is no boy-girls like this, what is not stable, that you can find a boy and a girl that were not matched to each other, but they prefer each other on what they got. In that case, this is not stable. So what is stable? It is a matching which is not stable. You cannot have such a case. Is there a stable match for every set of boy-girl preferences? That's the question that actually David Gale wrote a letter, I think it was in 1959, to Lloyd Shapley. At that time, Lloyd Shapley, as I said, David Gale was in Berkeley, and he asked, he could not solve the problem. He asked people in the department of math department, is it true that always I can find a stable matching? And nobody could answer. But he knew of Lloyd Shapley. At that time, he worked for the Rand Corporation in Santa Monica. And then he sent him a mail. There was no email, no computers. I mean, just the beginning. But 1959. So he sent a letter. The letter arrived to Lloyd Shapley. He opens up and read the problem. And in a day or two, he solved the problem completely. And both of them then made a lot of contribution about it. But they say that they found that there is always stable matching. And typically it's not unique. Sometimes it's unique, but sometimes you may have 5 different stable matchings. We are going to talk about 2 very, very important ones. We'll talk about it later. Yes, the answer. Here it is, the Deferred Acceptance algorithm. That's the algorithm found by Gale and Shapley, described by Gale and Shapley in a paper in 1969. They published the paper 2 years after or something like this, but they start talking about the problem or exchanging mail in 1959. And the idea, what is the algorithm? I'll tell you, the algorithm is a beautiful one. It's called the Deferred Acceptance algorithm. And it basically, either boys run after the girls and girls are passively waiting for the boys, or oppositely, girls runs after the boys and the boys patiently waiting for an offer. So that will be very interesting, and by the way, we can draw some interesting conclusions. Before elaborating on this algorithm, it should be noted that only 2-sided markets are guaranteed to have a stable matching. One-sided markets are not. Sometimes it has, sometimes it doesn't have. So we want to make two-person teams from two-person teams from this group. So we have Al, Bert, Clive, and Gus. Okay, and actually, and their preference, I think that there's one that, suppose that Gus is matched with some X. Okay, but you know what? I don't want to get into this. I just want to say that if everyone can rank everyone, not that you have boys different than the girls, but you have Al here and Al here, Bert and Bert, Clive and Clive. Okay, in that case, okay, you may not have a stable matching. What and this example, you can read it later on. This example shows that if, for instance, if the boy and the girls, but the boy can rank not only the girls, but also the boys. You can say, I prefer that boy on that girl, but that girl on that boy. They can rank all of them. Then it is a one-sided market. Typically, you may find examples where there is no stable matching. So what Lloyd Shapley and Gale and Lloyd Shapley proved that there is always stable matching if we have two-sided markets. Boys, girls, doctors, hospitals. Okay, this joint set of people or employees and employers. Okay, so and you can it explains exactly, but I don't want to push that much. That example. Now, so what is DAA? Deferred Acceptance Algorithm, with boys proposing. So girls are sitting at home and waiting, and boys proposing to the girls. Okay, so let's start. So day one, every boy, this is the algorithm now. In day one, every boy proposes to the first girl on his list. So all the boys are very ambitious. They go to their top on the list. Now, what can happen? It can happen that some girl get more than one boy. Okay? And it can happen that, for instance, Betty will get Barry and Claude, because Barry, number one of Barry is to go to Betty. Claude, number one, go to Betty. So Betty may get two. What she does is the following. She compares what she prefers. Let's say in this case, she gets two. She gets Barry and Claude. Claude is better than Barry. And first of all, she sends a ding to Barry, namely, you're out. What about Claude? You stay here, okay, temporarily. If nobody will come later in the day after, will not come to me, then I'll keep you. But if somebody better will come to me, I'll kick you out. So it is a temporary acceptance, okay? So deferred acceptance. I don't accept you now, but but if I don't find anything better than you, then I'll accept you. And what happens if a girl gets exactly one? Then she says, wait, if I don't get somebody later on, somebody better, I'm going to be matched to you. And what happens if a girl doesn't get anyone? She's waiting. What can she do? Okay, so let's see how it works in day one. So Adam goes to Daisy, because Daisy is number one for Adam. Barry will go to Betty. But also Claude goes to Betty. And Dave goes to Anne. Good. So now, in day number two, Betty is going to reject Barry. Every girl asks his favorite boy among those who propose to come again the next day, or to stay. I use the version stay with me unless I'm going to reject you down the road. So if you like, come again or stay until I don't find somebody else better than you. And rejects all the others. So Betty, she's going to reject Barry. And now the rejecting people in the next day, they go to their second on the list because they were rejected from the first on the list. Here it's only one. Okay, so Betty send out Barry. So Barry will go to whom? To number two on the list. Day number two, Barry moves from Betty to Anne. Day two, all boys who were asked to come again, do so. Or if you like, stay, and if they were not rejected. And rejected boys go to the next girl on their list. So Barry will go to, Barry will go to Ann. So in the next day, that is the table that goes like this. And now Ann has 2. Okay? But Ann now says, wow, Barry number 2, not bad for me, but Dave was number 1. So she's going to send Barry out. So Barry moves from Betty to Ann, but Ann will send him out, and he will go to whom? To Daisy. Here's Barry. Barry and Saturday, day 3, ditto. Barry goes to Daisy. Why? Because she is number 3 on his list. He was in number 1. She rejected him. He went to number 2. She rejected him and rejected him. And now he goes to Daisy. So that's the map in day after day number 3. Now Daisy looks and say, I got, she had before Adam, number 4. But she prefers Daisy, Daisy prefers Barry on Adam, because Adam is number 4 for her and Barry is number 3 for her. So now she, in day 4, she is going to reject Adam, and Adam will go to number 2 on his list. Now we finished, because every boy has a girl and every girl has a boy, and this must be a stable match. And I would like to explain why. But first of all, so what is the match? Adam is matched to Carol, Barry is matched to Daisy, Claude is matched to Betty, and Dave is matched to Ann. So look what happens to the boys. Dave got his number 1. Claude got his number 1. Adam got his number 2. And Barry number 3. Not that bad. Good for the boys. Let's see what happens to the passive girls. All of them get number 3 on their list. Oh, that's too bad. Is there something general here? The answer is yes, but I'll come to that very soon. But this is the why it is a stable match or matching. Let me explain. Suppose, so forget about this specific example. I want to give you, so what is the algorithm? The algorithm, again, maybe you have 50 boys and 50 girls, or more boys than girls, or whatever. But let's say boys and girls. Let's say that the girls are the passive, boys are running after the girls, namely the boys proposing. So in the first day, all boys go to their first on the list. A girl that did not get anyone waits. A girl that get one, say to the one, you are a candidate. If I don't get a better one, later down the road, you'll stay. I'm going to be matched to you, but I may throw you out if I'm getting something better. A girl that get 2, reject the one that, maybe a girl can get 5. So she leaves the one that she likes the most among the 5 that she got and reject all the others. Next day, those that stay. But the rejected boys now go to the second on the list. Okay? Now they may push somebody that was not rejected before, because that girl may get now some rejected boy that she prefers on what she had before. Okay? So all rejecting boys goes to the second on the list, and again I do the same thing. Every girl now looks what she has. If she has nothing, she's waiting. And if she has two or one or more, she rejects. If she has more than one, she rejects all the boys that she, or to say it differently, she will leave the boy that she likes the most among those that came to her, and she will reject all the others. And if a girl gets only one, she tells the one, okay, she may be let's say only one, or maybe that guy was before, or maybe before she has no one, but one of the rejecting boys come to her. Let's say she has one. She tells the one, you stay, but I cannot promise anything. Third day, the rejected boys are going from day number 2, going to their number 3 on their list, and blah blah blah, until until all boys, if they are the proposing, match to all girls. So if there are, let's say, 4 boys and 5 girls, if the 4 boys, obviously you cannot match all boys to all girls because you have 4 boys and 5 girls. But once all boys get girls, 4 boys, let's say, get 4 girls, the procedure stops and you get a stable match. Why it is a stable match? Now, follow carefully. Suppose that there are 2, let's say, is it possible that there are 2, boy and a girl, that were not matched to each other, but they preferred each other? Okay? So if, let's say, and there is a girl that I'm Yair, and there is a girl that Alice, okay? And we were not matched together, but I prefer Alice on what I got, and she prefers me on what she gets. That's impossible, because if I prefer Alice on what I got, by the algorithm I visited her. Why? Because first I visit number 1 on the list. I reject him. If I'm rejected, number 2, then number 3. So if I end up with, let's say, number 6, and Alice was before, because what the idea is it possible that I prefer Alice on what I got? So she is ranked higher than what I got. Since I go from the best one down, it must be that I went to Alice. So why I didn't finish with Alice? Because Alice rejected me. I mean, why I went down from Alice? Because Alice rejected me for a better boy. And maybe she didn't even end up with that boy. Maybe she got even better later on. But in any event, she eventually ended up with somebody that she prefers more than me. So it cannot, if I prefer Alice on what I got, Alice does not prefer me. In that case, there's no objection. There's no boys and the girl that do not match to each other. If the boy prefers the girl does not prefer the boy. If she was not matched to him, that means that she rejected him. He prefers her, he visited her. Why he did not end up with her? Because she got a better one and rejected him. And therefore she will end up with a better boy. As easy it is, this is a stable match. Good, but now we can also ask what happens if girls running or proposing to boys. That may end up with another stable match. This is a stable match or matching. DAA with boy proposing summary. Every day, each boy, so this is the algorithm, I told you, now it's written, each boy proposes to his favorite girl among those who have not yet previously rejected him. Okay, so no matter, so each boy proposes to his favorite girl. If he was rejected by girls, obviously he cannot come back. So he proposes to the best on the list after being rejected so far. So among those who have not yet previously rejected him. Every girl who has more than one proposers rejects everyone except the proposer she likes the best. Theorem, that's what I said. For any boy-girl preference, the boy proposing process ends with a stable matching. I proved it to you. And this again a proof, exactly what I told you. So I don't need to go through. Now I want to talk about deferred acceptance algorithm with girl proposing. So let's try now. So boys sit at home, girls goes after the boys. So Anne will go to Adam. He's number one. Betty also will go to Adam. Carol will go to Barry. And Daisy will go to Claude. Dave has nothing, so he have to wait. These two, Anne and Betty that visited Adam, he will reject Betty, etc. Let's see how it works. Actually, this algorithm end up very fast. Let's see. In this case, day one, Daisy go to Claude. He's on number one. Carol goes to Barry, number one. Betty will go to Adam, number one. Adam and Anne goes also to Adam. So Dave can do nothing. Claude says to Daisy, maybe I'll get you, but let's see if I don't get something better. So meanwhile, wait. Barry said to Carol, meanwhile, wait, but I may get better. What Adam says to Betty, look, I got somebody better than you, I reject you. And he says to Anne, maybe I'll end up with you, but unless I'm going to get better one from other rejected boys. From other rejected girls. So Betty is rejected. Day two, Betty is rejected, correct? And therefore she goes, Betty went to number one on her list. Now she goes, should continue here, she goes to number two on her list, where she goes to Dave. Up, finished. Every girl got a boy, every boy got a girl. This is a stable matching. But look what happens here. Look what the boys got. Adam got number 3, Dave got number 4, Barry got number 4, Daisy got number 4. Very bad for the boys. What about the girls? Anne got number 1, Carol got number 1, Daisy got number 1, and Betty number 2. Perfect for the, almost perfect for the girls. Very bad for the boys. Is there a general theorem about it? Okay, so that's the question. So now let us combine the two deferred acceptance algorithm with the girl proposing and the boys proposing. So as you can see, we combine them two. The yellow ones are the boy proposing, and the green ones, is the girl proposing matching. And we can see that when the girl proposing, the matching of girl proposing is very good for the girls, very bad for the boys. Opposite, more or less, is the case where boys are proposing. It is very good for the boys, very quite bad for the girls. As I asked the question, is there any general theorem behind it? And the answer is yes. So first, before I'm going to the theorem, let me just, I want to make sure that you understand that we found two stable matches. One where boys proposing, the other one is when girl proposing. But by no means there are only two. By the way, the two may be one. It may be the same. Sometimes it coincides. We'll talk about it later. But is there a third one? Even in that example, the 4 boys, 4 girls example that we have right now, there is a third one. In general, there may be a lot of stable matches. We just point out 2, and as it will be shown in a minute or 2, these 2 are extreme ones with very important properties. Okay. So first of all, let me just mention that the third one, you can check yourself. Actually, I'm going to show you, but I'm going to skip it just on the slide. You'll see it, how to get it. But however, another stable matching is where Adam is paired with Anne, Barry is paired with Carol, Claude is paired with Betty, and Dave is paired with Daisy. So that was not the possibility of Dave and Daisy together. There was not in either one of the 2 before. But Adam and Anne was paired in with the girl proposing algorithm, and Claude and Betty were paired in the boys proposing algorithm. So this is a mismatch in a sense. I mean, you have a new stable matching, and one of them is that Dave and Daisy were not matched in either one of them. But you can check, it takes a time, but you can prove that in this specific example we have only 3 stable matches. If I would have, 1,000 boys and 1,000 girls, I may have hundreds or maybe even thousands of stable matches. So there are a lot. We focus only on 2 of them. Boys proposing DAA, girls proposing DAA, Deferred Acceptance algorithm. So this is to explain what's going on with the new one. I don't want to spend time on that. You can do yourself. But here is a theorem, a very important theorem. In boys proposing Deferred Acceptance algorithm, all boys are paired with their most preferred choice. But what does it mean, most preferred choice? My most preferred choice is number 1. Among or compared with all stable matches. So let's say that we have 50 stable matches, and I'm looking on, let's say, Adam. I look what Adam got in all these 50, all possible girls that Adam got in all stable matches. The best that he could get is in where boys are proposing. Okay, in that stable matching that is obtained by both proposing Deferred Acceptance algorithm. At the same time, and this is not only for Adam, all boys uniformly, all of them get the best they could dream compared to all possible stable matches. Not whatever, I'm getting the best. It cannot be that all boys get number 1 in general. However, if you compare what every boy is getting in all possible stable matches, every boy is paired to his best choice compared to all possible stable matches. At the same time, all girls obtain the worst, the least preferred, compared with all possible stable matches. So this, when boy proposing, it's really some extreme. All boys get the best, all girls at the same time get the worst. What happens if girl proposing? Obviously, it's symmetric. The girls getting the most preferred choice compared to all stable matches, and at the same time the boys are getting the worst they can get in all stable matches. So again, just to make sure that we digest it, I want to read with you the theorem. In boys proposing deferred acceptance algorithm, all boys are paired with their most preferred choice. What does it mean, most preferred? When I compare, just look on all stable matches. At the same time, all girls are paired with their least preferred choice compared with all stable matches. So the boys are picking up, their choice, which is, if the boys are proposing, they get their best they can dream in any stable matching. Look, if it's not stable matching, then everything collapses until they get to a stable matching. So I have to compare just stable matches. And when boys are active and they are proposing to the girls are passive, boys getting the best, girl gets the worst. And opposite. If the girl proposing, they take initiative, they are active, they get the best, and all the boys get the worst, all the girls get the best. Best or worst relative to all stable matches. So, if you are looking for a job, don't stay at home and waiting for them to call you or to approach you. Take initiative, be active, go after them. Don't wait to them to approach you. That's the message. And there is a proof. I don't want to get now into the proof. I'm going to give you an example in a second. Now, what is BP boy proposing deferred acceptance algorithm, and what if and girl proposing deferred acceptance algorithm overlap? What happens if the two of them are the same? Okay, that means boys proposing and girl proposing yield the same stable matching. That means that the conclusion is there must be a single stable matching. If the two extreme, because everything is in between. Why? Let's say this is the boy proposing. So they get the best and the girl the worst. Opposite completely if the girl's proposing. Boys get the worst, girl get the best. If they are the same, if the worst is the same as the best, there's nothing in between. It must be the only stable matching. If you figure out, you find the boy proposing DAA and then the girl proposing DAA, and you find that they are the same, you don't need to, that implies by the theorem before, that there is only one stable matching for this example. If there's only one stable matching, it is clear that that explanation, it's clear that both procedures yield the same matching, the only stable one. What they mean here, if there is only one stable matching, so it's clear that both procedures, both algorithm yield the same matching because they are both stable. So there is only one stable because, as I said, there are two extreme and nothing can be in between if they coincide. Suppose that both procedures yield the same matching in which Brenda, now it's an explanation, Brenda and Dylan are paired. Since this is the result of boy proposing and so the boys, let's say that Brenda and Dylan are paired in the boy proposing algorithm. And in actually the same, because both matches are the same, they coincide. So in particular, Brenda and Dylan are matched in the boy proposing DAA. So Brenda is Dylan's favorite girl of those feasible for him. So in all the stable matches, Brenda is Dylan's most favorite girl, because this is a result of boy proposing. Boy proposing, all boys gets the best they could get. At the same time, since this is the result also of the girl proposing, Brenda is Dylan's least favorite girls of those feasible for him, namely from all possible stable matches. Therefore, Brenda is the only feasible girl for Dylan, feasible in the sense that they can be matched in any of a stable matching. So if Brenda is the best and also the worst for Dylan, Brenda is the only one for Dylan, and the same for everyone else. Hence they are paired in every stable matching. Now I want to give you an example. The example, let's take the example of 5 boys, capital A, capital B, capital C, capital D, and capital E, and 5 girls denoted by small a, small b, small c, small d, small e. The preference of every individual, boy or girl, is given by. So look on the boys. Let's look on boy A. Boy A prefer girl B the most. Second best for him is E. Third best is D. Fourth is A. Last is C. So that is the ranking of A. What is the ranking of B? He prefers girl A first, then B, then C, then D, and the last is E, etc. Here we have the girls. Girl A prefer boy A on B, on C, on D, on E. E is the worst, A is the best. Girl B prefers B on E, on D, on C, on A, and everything is there. I want to find out first what are the first the boy proposing DAA, and what is the the result of what is the stable matching resulted by boy proposing DAA, and what is the stable matching resulted by girls proposing DAA. Okay, so let's see how it works. Okay, so let's now talk about DAA with boys proposing. What happens? Girl sits at home passively. In the first day, all boys go to the first on their list. So A goes to B. Here is A is going to B. Next, boy B goes to A. So boy B goes to A. Okay? Now, boy C goes to girl E. Boy C is going to girl E. Boy D goes to A, so also D goes to A. And then boy E goes to B, so B actually getting 2 boys, A in E, A and E. 2 boys. Girl, we're talking about girl A. Girl A is here and here. B and D go to girl A. Girl B is getting also 2 boys, A and E, A and D. And girl E gets C. C and D don't get anything in the first day. Okay, so in the first day it looks like this. So now C and D cannot do anything. Girl E tells C, stay meanwhile, maybe I'll replace you by somebody later on that I will prefer on you. So let girl A now that has 2 boys, B and D. Here is girl A. She has 2 boys, B and D. As you can see, she prefers B on D, and she rejects D and tell B, you stay here. Maybe that you will be my choice. If somebody else better, who can be better, A, will come to me, then I'll kick you out. Okay, and tells, so B meanwhile stays. Girl B has also a conflict. A or E? So she looks girl B, A or E. She likes E more than A, and she gets rid of A. Okay? Now, in the next day, the rejected boys, D and A, go to the second on their list. So who are the rejected boys? D and A. They go to the second on their list because A was rejected by B and D was rejected by A. So D and A going to the second, it's the same one. They go to E. So in day number 2, E gets 3. C from before, D and A. B and E, I mean girls A and B, still nobody new came to them, so B and E is still there. So now the question, where C and A go? So C, okay, because first of all, C, D and A. So I look on E, and E actually, and she has to make a choice between C, D and A. C, D and A. She prefers D, so she kicked out C and A. In day number 3, C and A looking for a girl. So C that used to be in E, his first choice, now moving to his second choice. Okay? So C moves to C. His second choice is girl C. So C moves from here to here. A that is rejected by E, A rejected third time. A was rejected from B, now from E, and now he's going to his first one, D. So A goes to D. We have, as you can see, every boy has a girl, and it must be, and every girl has a boy. So it must be, that is a stable matching where boys proposing to girls. So this is the summary, this is the case. Okay, now do the same thing where boys are waiting at home. And by the way, just let's look on what's going on here. A got D, third on his list. It means that he cannot get B on E because this is the best that he can get in any stable matching. That's what we proved before. B got A, quite good. C got C, not bad. D got E, not bad. And E got B, quite good. What about the boys? These are the boys. What about the girl? Girl A got B. Girl A here got B, second on her list. Girl B, got E. Girl B got E, second on her list. Girl C got C, first on her list. Girl D got A, second on her list. And girl E got D, third on her list. Okay, so this is what we got here, and and now let's do what is the girl proposing DAA. Okay, let's see. So boy sits at home. In the first day, every girl go to her top of the list. So girl A goes to A. So A get A. Girl B goes to B. So B is in B. Girl C goes to C. Girl D goes to E. D goes to E. And also E goes to E. So boy E is getting 2. The rest getting 1, and D does not get anyone. So the first 4, A, B, C, D, cannot do anything. They're just waiting. Girl E that got 2 of them, boy E that got 2 girls, D and D, need to compare what he prefers more. We're talking about boy E. D or E? D or E? He prefers D on E. So he will get rid of E. Okay, so he will tell E, I reject you, and tells D, you meanwhile stay. Maybe you'll stay forever, but may not if I get something better down the road. Good. So now girl E that was rejected from boy E, she goes on second on the list to B. So she goes to B. So now actually B gets 2. In day number 2, A stays with A, B now got another one, E, C with C, did not get any, and E with D. So now we look, B looks what he prefers, so B looks B or E, B or E. Obviously he rejects E and leave B. So E has to go to the third on her list. She goes to D. So E goes, here is D, here goes to D, and now, E goes to D, and now every boy have a girl and every girl has a boy. So that's it. So A is paired with A, B with B, C with C, D with E, and E with D. Let's look what's going on here. I can say, look on these two. They got the same, this is the same pair, whether it is boy proposing or girl proposing. I conclude that in every stable matching, maybe here there are 6 stable matching. I don't know. I didn't compute it. But I can tell you, no matter what stable matching you'll give me, beside these two, C must go with C, and D must go with E. Why? Because you get the same 2 pairs in both you get it from the same 2 algorithm, where one's boy proposing, the other one the girl proposing. Why it is like this? Because look here, these are the boys proposing. So C is the best for C. Remember, small c is the best for capital C. Why? Because here the boys are active and they get the best for them in all stable matches. So girl C is the best that C can get. When I go down to the girl proposing, I'm getting also C and C, but now the passive one, the boys, are getting the worst. So girl C is the worst for C from here. At the same time, girl C is the best for C. So if it is the best and the worst, C cannot get something else. Okay, so capital C, the boy C cannot get something better and something worse. Okay, because he gets in both cases the same thing. It's the best and the worst, so it's unique. Conclusion, in every stable matching, boy C will be paired with girl C, similar to boy D with girl E. So let's see what we can draw a lesson. Let me analyze the result that we have. What can we say about A, B, C, D, E boys, and the same for the girls? Okay, so let's look on boy A. In the boy proposing, he got girl D. So girl D must be the best he can get in any stable matching. So she is the best. And let's go now where the girl proposing, A gets A, but when girl proposing, boys get the worst they can get. So so if you like, D is the best for A. And A is the worst for A. What we conclude? So we look on A, look here. D is the best, A is the worst. So A cannot be matched to C because, so let me put the B for best and for A the worst, W. So C, he cannot get in any stable matching C because A is the worst for him. in all stable matches. He cannot get better than D, because D is the best compared to among all stable matches. So I can tell you for sure, there's no stable matching where A gets B, E, or C. A can't be matched to either B, E, or C in any stable matching. That's the conclusion for A. Let's go for this exercise. I'm sure that you'll see it also in the exam, so I want to make sure that you understand it. Remember, when boy proposing in that algorithm, boys are getting the best they can get in all stable matches, and girls at the same time get the worst. Opposite, if girl proposing, girls get the best, boys get the worst. Okay, let's go to boy B. Boy B is getting, the best is A, the worst is B. Let's see, the best is A, the worst is B. So he cannot get C, D, and E. B can't be matched to either, D, E, or C, E, or D. Boy B cannot be matched to, the order is not important, C, D, or E. Good. In any stable matching. Let's go to C. What C gets? In the boy proposing, C gets C. In the girl proposing, he gets C. C for sure will get in any stable matching, girl C. Must be matched to C in every stable matching. Let's go to D. What D got? D got E and E, the same thing. So in any possible, D must be matched to E in every stable matching. Let's talk about E. E got, let's look on here, that's what E gets. The best for him is B, the worst D. The best B, the worst D. So I can tell you, he cannot, what he cannot get is E. That's what I can say. Why? Maybe he can get in a stable matching A. D is the worst, B is the best. Maybe in one stable matching, he can get A or C. But I can conclude, E can't be matched to E in any stable matching. Is there a stable matching where E is matched to A? Maybe. One has to find all the stable matches. By the way, you can do it in using a simple algorithm to find, with a computer to find all stable matches. If it's not too large, you can do it. In any event, then you can see if E can be matched to A or C. But he cannot be matched to girl E, because the worst for him is D. Now let's look on the girls. So I'm looking on girl A. Here is girl A with A and girl A with B. So B is the worst, because this is the boy proposing. Girl A get the worst for her. So B is the worst for A. This is the worst. And A is the best for her. Great. So she cannot get C, D, or E. A can't be matched to either C, D, or E in any stable matching. Okay. B, let's talk about girl B. B is here and B is here. The worst for B is E, the best for B is B. B is the best and E is the worst. She cannot get DCA. B cannot be matched to DCA or CDA. Okay. Girl C. Let's talk to girl C. C is matched to C in both cases. C must be matched to C in every stable matching. Great. Let's talk about girl D. Girl D, she is matched here with E and here with A. The A is the worst, because this is the boy proposing. D gets A, the worst, and she can get E, the best. Let's look on girl D. E, the best, and A, the worst. She cannot get CDB. Can't be matched to either CDB in any stable matching. Finally, let's talk about girl E. Girl E is getting in both cases D, and therefore she must be matched to D in every stable matching. I hope that I clarified the theorem and the algorithm, And let's talk about Lonely Hearts Club.